All right, get ready, because today we're going deep into A-levels nuclear physics.
Specifically, the AQA syllabus.
That's right.
Yeah.
I know it can sound a bit intimidating, but trust me, this stuff is really mind-blowing.
Once you kind of get past the
scary-sounding name.
scary sounding name, yeah.
Exactly.
It's like peeking behind the curtain of reality
Yeah.
and seeing how the universe is built
At its most fundamental level.
at the tiniest level. And the best part is it's not just theoretical.
Yeah.
Nuclear physics is behind everything,
Right.
from medical breakthroughs to the way stars shine.
Okay, so let's start with a little trip back in time.
Okay.
Imagine scientists picturing the atom as this plum pudding.
Plum pudding.
Who comes up with these analogies?
You have to remember they were working with very limited information back then.
Yeah.
The plum pudding model basically said that the atom was this positively charged blob with negatively charged electrons just sprinkled throughout.
Like plums in a pudding.
Like plums in a pudding, exactly.
Yeah. Delicious, but not quite right.
Not quite right, no.
Then came Rutherford.
Rutherford.
And his gold foil experiment.
Yes.
Which completely blew this plum pudding idea
Out of the water.
out of the water.
Rutherford's experiment was so simple,
Yeah.
yet so brilliant.
Okay.
He fired these tiny alpha particles at a thin sheet of gold foil.
So it's like a microscopic...
It's like a microscopic game of atomic darts.
Yeah.
And surrounding the foil was this fluorescent screen,
Right.
so they could track where the alpha particles landed.
Okay, so we've got our alpha particles.
Yeah.
We've got our gold foil target.
Yes.
What happened next?
Well, most of the alpha particles passed straight through the gold foil.
Oh, really?
Like, it was barely even there.
Okay.
But here's the kicker. A small number of those alpha particles were deflected.
Really?
Some even bouncing straight back.
Wow.
It was totally unexpected.
So these tiny particles were somehow repelled by something inside the gold atom.
Inside the gold atom.
What could be strong enough to do that?
That's the question that Rutherford grappled with.
Right.
And the only explanation was that there had to be a tiny, incredibly dense, positively charged nucleus
Okay.
at the center of the atom.
Right.
Most of the atom was empty space,
Okay.
which is why most of the alpha particles just sailed right through.
Right.
But those that got close to the nucleus
Yeah.
experienced this strong repulsive force.
So no more plum pudding.
No more plum pudding.
This basically revealed the atom's true structure
Yeah,
with a nucleus at its heart.
exactly.
That's a pretty big deal.
Absolutely massive. It was a paradigm shift
Wow.
in our understanding of matter.
Okay.
And it set the stage for everything that followed in nuclear physics.
So
It was like discovering a whole new continent,
Right.
a tiny, powerful continent at the heart of every atom.
Okay, so we've got our nucleus.
We've got our nucleus.
But things get even more interesting when we realize that some of these nuclei aren't exactly stable. Enter the mysterious world of radiation.
It's like some of these nuclei are bursting at the seams with energy,
Okay.
and they release it in the form of radiation.
Yeah.
But here's the thing. There are different types of radiation, each with its own unique properties,
All right.
and even uses...
So how do we figure out what kind of radiation we're dealing with?
Well, there's a classic experiment
Okay.
that uses different materials to filter out the radiation.
Okay.
Imagine you've got this mystery radioactive source,
Okay.
and you want to know what it's emitting.
Okay. I'm intrigued. Lay on me.
First, you try a simple sheet of paper.
Okay.
If that stops the radiation, you know you're dealing with alpha particles.
Alpha particles?
They're relatively large and heavy,
Okay.
so they're easily stopped by something as thin as paper.
So alpha particles stop by paper.
Got it. Yeah.
What if the paper doesn't do the trick?
Then you bring in the aluminum foil.
Okay.
If that stops the radiation, it means you're dealing with beta particles.
Beta particles.
Much smaller and lighter than alpha particles.
Okay.
So they can penetrate paper,
Yeah.
but are stopped by the denser aluminum foil.
All right. So alpha paper, beta aluminum foil.
Exactly.
What if this radiation is a real powerhouse and even the foil can't stop it?
That's when you call in the big guns.
Okay.
Lead. If
Lead?
a thick block of lead can stop the radiation,
Yeah.
you know you're dealing with gamma radiation.
Gamma.
This is super high energy electromagnetic radiation,
Right.
like an incredibly powerful X-ray.
Okay.
It can travel long distances and penetrate most materials.
Right.
So you need something dense like lead to block it.
So it's like a radioactive obstacle course?
It is a radioactive obstacle course.
But it's not just a cool science demo, right?
No, it's not.
This kind of radiation identification has practical uses.
You bet. For example, think about something as mundane as aluminum foil.
Aluminum foil.
You want that foil to be a consistent thickness, right?
Right.
Well, beta radiation can be used to monitor the thickness of the foil during production.
Wow.
It's like a radioactive quality control system.
That's pretty clever.
Yeah.
It's amazing how we can harness these different types of radiation for such specific purposes.
Exactly. And when it comes to gamma radiation, the medical applications are incredible.
Okay.
Gamma rays are used in medical imaging scans to see inside the body.
Wow.
They can sterilize surgical equipment.
Right.
And they're even used in radiation therapy to target and destroy cancer cells.
It's amazing how something that can be potentially dangerous can also be so beneficial.
Precisely.
When used in a controlled way.
But it's a good reminder that even with its beneficial uses, gamma radiation is powerful stuff.
Yeah.
It's important to remember the inverse square law.
Okay.
The intensity of radiation decreases rapidly with distance.
Right.
So the further you are from a source of radiation, the safer you are.
Okay, that's good to know.
So
we've got these radioactive nuclei.
Yeah.
But they're not exactly sitting still.
Oh.
They're constantly changing through this process called radioactive decay.
Radioactive decay.
It's like a constant race against time.
It is.
For these unstable nuclei.
Absolutely. Radioactive decay is all about unstable nuclei trying to find a more stable configuration.
So are we talking about like a nuclear makeover here?
You could say that. And every radioactive substance has this characteristic called a half-life.
Half-life.
The time it takes for half of the radioactive atoms in a sample to decay.
Okay, so if we start with, let's say, 100 grams of some radioactive substance.
Right.
With a half-life of 1 hour.
1 hour?
After that hour, we'd have 50 grams left.
Exactly. After another hour, you'd be down to 25 grams.
Okay.
Then 12.5 grams and so on.
So it's like a radioactive countdown.
It's a radioactive countdown.
Yeah.
And you know how archaeologists can date artifacts that are thousands of years old?
Yeah.
They use the half-life of carbon-14.
Wait, so carbon-14 is like a built-in radioactive clock?
It is.
For ancient objects. That's incredible.
It is pretty amazing.
And how does that even work?
All living things absorb carbon-14 from the atmosphere.
Right.
When they die, that absorption stops and the carbon-14 starts to decay at a known rate.
Right.
So by measuring how much carbon-14 is left in a sample, scientists can work backward and figure out how long ago that organism was alive.
So it's like a time machine.
It's a time machine for history.
That's mind-blowing. But I'm guessing it's not always as simple as looking at a clock.
You're right.
Isn't radioactive decay a random process?
It is a random process. We can't predict exactly when any individual atom will decay.
Right.
It's like trying to guess when a single popcorn kernel will pop.
Yeah.
But statistically, when you have a large sample, you can predict the overall behavior.
So it's like flipping a coin. You can't predict a single flip.
Yeah.
But over many flips, you'll get a pretty even split of heads and tails.
That's a great analogy.
Okay, good.
But here's another question. If the strong nuclear force is supposed to be holding the nucleus together, why do some nuclei even decay in the first place?
Yeah, I was wondering that too. It's like, if the glue is supposed to be so strong, why are some nuclei falling apart?
It's a balancing act, really. Remember, while the strong nuclear force is holding the protons and neutrons together, those protons are all positively charged.
Right.
And, like, charges repel each other.
So it's like a constant tug-of-war.
It is.
Inside the nucleus.
Inside the nucleus.
Strong force is trying to hold everything together.
Yeah.
But the protons are pushing each other away.
Exactly. And there are a few things that can tip the scales towards instability.
Okay.
One is the neutron-to-proton ratio.
Okay.
Too many protons and the electromagnetic repulsion becomes overwhelming.
Yeah.
Too many neutrons and the nucleus becomes neutron-rich.
Right.
And unstable.
I'm trying to picture this. It's like trying to cram too many magnets together.
Yeah.
The kind that repel each other.
Uh-huh.
The more you force in, the more unstable it becomes.
That's a great way to visualize it. And to regain stability, those unstable nuclei undergo different types of radioactive decay, each addressing a specific type of imbalance. We've already talked about alpha, beta, and gamma radiation.
Right.
But now let's look at how they fit into this picture of nuclear instability.
Okay, let's break it down. Alpha decay, if I remember correctly, is like the nucleus ejecting a chunk of itself.
That's right.
To slim down a bit.
This chunk is an alpha particle, which is essentially a helium nucleus.
Okay.
2 protons and 2 neutrons.
Right.
Alpha decay is a way for very large, heavy nuclei to reduce their size and become more stable.
So it's like a nuclear weight loss program.
You could think of it that way.
Yeah.
Now, beta decay is a bit more complex.
Okay.
It comes in two flavors, beta minus and beta plus.
Okay.
In beta minus decay, a neutron in the nucleus decides to switch teams and become a proton.
So it's like a nuclear identity crisis.
It is a nuclear identity crisis.
What happens when a neutron becomes a proton?
Well, it changes the neutron to proton ratio, making the nucleus more stable.
Okay.
In the process, the nucleus emits an electron called a beta minus particle and an antineutrino. And beta plus decay is the opposite. A proton turns into a neutron.
Okay.
In this case, the nucleus emits a positron, the antimatter counterpart of an electron and a neutrino.
Wow.
Again, it's all about adjusting that delicate balance of protons and neutrons.
So beta decay is like fine-tuning the nuclear recipe.
Exactly.
What about electron capture?
Electron capture.
I remember reading about that in the AQA material.
Good eye. Electron capture is another way for a nucleus to reduce its proton count.
Okay.
It's like the nucleus grabs an electron from one of the atom's inner electron shells
Right.
and uses it to neutralize a proton, turning it into a neutron.
It's like a proton saying, hey, I need a hug.
Yeah,
And an electron comes in to save the day.
exactly. And then you've got gamma decay, which is a bit different.
Okay.
It's not about changing the number of protons or neutrons. Instead, it's about the nucleus releasing excess energy.
So it's like the nucleus is letting off some steam
Yeah.
after a stressful event, like alpha or beta decay.
You got it. The nucleus releases this excess energy in the form of a gamma ray photon,
Okay.
which is a high-energy electromagnetic wave.
And I bet there are medical applications for gamma decay too, right?
You're right. A great example is technetium-99 meter,
Okay.
a metastable isotope used in medical imaging.
Right.
It decays by emitting gamma rays, which can be detected to create images of organs and tissues.
It's amazing how we've learned to use these different types of radiation for everything from medical diagnosis to understanding the history of ancient civilizations.
It really speaks to the ingenuity and creativity of scientists. But there's another question that might be bugging you.
Okay.
How do we even know how tiny the nucleus is?
Right.
We're talking about something incredibly small.
Yeah, that's always boggled my mind.
Mm-hmm.
Is it like a grain of sand? A speck of dust?
Yeah.
How do you even measure something that tiny?
It's like trying to measure the width of a human hair with a ruler the size of a football field.
Right. How is that even possible?
Scientists use a technique called electron diffraction, which is kind of like shining a flashlight on a tiny object
Okay.
and studying the shadow pattern.
So we're basically shining a beam of electrons at the nucleus
Exactly.
and seeing how they scatter.
Yeah. And by analyzing the pattern of scattered electrons, we can figure out the size and shape of the nucleus.
Okay, so spill the beans. Just how small are we talking?
Hold on to your hat. We're talking femtometers.
Femtometers.
That's 1/4 of a meter.
Okay.
Put that in perspective, if the atom were the size of a football stadium, the nucleus would be about the size of a marble,
Wow.
sitting right there on the 50-yard line.
That's mind-bogglingly small. And this tiny nucleus contains almost all the mass of the atom.
Yep. And that brings us to one of the most famous equations in physics.
Here we go.
EMC at T.
I was wondering when this was going to come up.
Einstein's masterpiece.
Einstein.
Which shows the relationship between energy and mass.
Yeah, it's like the equation everyone's heard of but might not fully understand.
You could say that. And what it basically means is that mass can be converted into energy. Right.
And vice versa. A tiny bit of mass can release a tremendous amount of energy.
Okay.
And that's what happens in nuclear reactions.
So this is where we get the immense power of nuclear weapons.
Yeah.
And on a more positive note, nuclear power plants, right?
Exactly. When a nucleus undergoes fission or fusion, a tiny amount of mass is converted into a huge amount of energy. It's like unleashing the energy that binds the nucleus together.
Okay, I need a visual here. What exactly is happening during fission and fusion?
Picture this fission is like splitting a heavy nucleus, like uranium, into two or more smaller nuclei.
Yeah.
Fusion, on the other hand, is like combining two light nuclei, like hydrogen, to form a heavier nucleus.
So fission is like breaking a chocolate bar into pieces?
Yeah.
And fusion is like squishing two pieces of clay together.
Perfect analogy.
Yeah.
And in both cases, energy is released because the binding energy per nucleon changes during these processes.
Okay, hold on. Back up a second. What's binding energy per nucleon?
Imagine you have a nucleus with, say, 10 nucleons.
Protons and neutrons combined.
Okay.
And a total binding energy of 100 units.
Right.
The binding energy per nucleon would be 10 units per nucleon.
Okay.
It's like the average energy holding each nucleon in the nucleus.
So it's like the glue strength per piece.
Exactly.
In our chocolate bar analogy.
Exactly. And when a nucleus undergoes fission or fusion,
Yeah.
those nucleons rearrange themselves into configurations with higher binding energy per nucleon.
Right.
And that difference in binding energy is released as energy.
Okay.
A lot of energy.
So it's all about finding a more stable, lower energy state.
Precisely.
For those nucleons.
And this difference in binding energy per nucleon is what drives both fission and fusion. It's why we can harness the power of the atom for things like nuclear power plants, and let's not forget the stars.
The stars. It's amazing to think that the same process that powers the sun is also used here on Earth to generate electricity.
It really puts things in perspective, doesn't it? We're essentially harnessing the same forces that forge the elements in the universe. Now there's this handy graph called the binding energy per nucleon curve.
A graph.
Ah.
Don't tell me this is going to be another one of those complicated equations.
Relax. It's not an equation, just a visual aid. This graph basically shows how the binding energy per nucleon changes as you move across the periodic table. It's like a map of nuclear stability.
Okay, I'm game. What does this map tell us?
Well, it shows that elements heavier than iron, like uranium, tend to have lower binding energy per nucleon, making them more likely to undergo fission. Lighter elements like hydrogen and helium have lower binding energy per nucleon and are more likely to undergo fusion.
So iron is like the king of the hill when it comes to nuclear stability.
You could say that iron sits at the peak of the binding energy curve, representing the most stable nucleus. But let's get back to fission for a moment, specifically induced fission.
Induced fission, okay.
The kind we use in nuclear reactors.
Okay, that's where we deliberately make a nucleus split, right? How do we do that? Do we poke it with a tiny stick?
Not quite. We bombard it with neutrons.
Okay.
But here's the thing. Not just any neutron will do. You need a thermal neutron.
Okay.
Which has a relatively low energy to trigger fission.
Okay.
Higher energy neutrons tend to just bounce off the nucleus.
So it's like you need the neutron to be moving at just the right speed to be captured by the nucleus.
Exactly. Think of it like playing pool.
Yeah.
If you hit the cue ball too hard, it might just bounce off the other balls. But if you hit it with just the right amount of force, you can sink a shot.
Okay, I can picture that.
Yeah.
So when this thermal neutron hits the nucleus, what happens?
The nucleus becomes highly unstable and splits apart, releasing energy and more neutrons.
Oh, yeah?
And those newly released neutrons can then go on to trigger more fission events.
Right.
Leading to a chain reaction.
It's like a nuclear domino effect.
Mm.
But if this chain reaction keeps going, doesn't that lead to, a nuclear explosion?
Mm-hmm.
How do we control this beast?
That's where the concept of critical mass comes in.
Critical mass.
It's the minimum amount of fissile material, like uranium-235, needed to sustain a chain reaction.
Right.
If you have less than the critical mass, the reaction fizzles out.
Okay.
But if you have more, things can get out of control.
So controlling this chain reaction is kind of important, I'm guessing.
You could say that.
Yeah.
And that's where all those safety features in a nuclear reactor come into play. Things like moderators, control rods, and shielding.
Okay. Break it down for me. What do these safety features actually do?
The moderator slows down those high-energy neutrons released in fission, making them more likely to trigger further fission events. It's like the reactor's speed bump, keeping things moving at a safe pace.
And control rods. Are they like the emergency brakes?
Exactly. They're made of materials that absorb neutrons, so by inserting or withdrawing them, operators can fine-tune the rate of the chain reaction and the amount of energy produced.
So it's like a volume knob for the nuclear reactor.
You got it. And of course, they're shielding thick layers of concrete and steel that surround the reactor core, preventing radiation from escaping.
So it's like a nuclear safety bunker.
Yeah.
But what about the nuclear waste produced in these reactors? That's something that worries a lot of people.
You're right, nuclear waste management is a critical issue. Spent fuel rods, which contain the highly radioactive byproducts of fission, need to be carefully handled and stored.
And this waste stays radioactive for a really long time, right? Like hundreds or even thousands of years.
That's right. It's a long-term challenge, and we need to have robust solutions. One approach is to store the waste in deep, geologically stable repositories far away from populated areas and water sources.
So basically, we're encasing it in a super secure underground vault.
Exactly. And there's ongoing research into advanced recycling techniques that could potentially reduce the volume and radioactivity of the waste. It's a complex issue with no easy answers, but scientists and engineers are working on solutions.
Well, this has been quite a deep dive into the world of nuclear physics. From the structure of the atom to the power of fission and fusion, we've covered a lot of ground. And I have to say, it's been fascinating, a little bit mind-bending at times.
It's definitely a field that challenges our understanding of the universe and our place in it, but that's what makes it so exciting. And as we wrap up, I think it's worth leaving our listeners with a question to ponder.
Yeah, hit us with that thought-provoking question.
As we grapple with the challenges of climate change and the growing demand for energy, what role will nuclear power play in our future? It's a complex issue with both benefits and risks, and understanding the science behind it is essential for having informed discussions and making wise decisions.
That's a great point. It's not just about the science itself, but about how we use that knowledge to shape our future. And on that note, we'll leave you to contemplate the fascinating and sometimes daunting world of nuclear physics. Thanks for joining us on this deep dive.